Okay, so maybe just to reiterate, it's not easy to follow along the slides if you're just staring at them in world, not easy to read them, but if you click on the screen, you'll get an overlay display which you can read. That's my son. You're very cute, but maybe get off my head. Okay. So deep learning is a family of differentiable algorithms, artificial neural networks being the obvious ones. But there's many more now than just the basic old school feed-forward networks. I won't go into what neural networks are. It's not that kind of talk. But they're used to both learn representations of data and compute with them. Compute with them meaning use them to make decisions or to classify objects or text or perform many other tasks. So a theoretical understanding of deep learning is, in my opinion, one of the most important mathematical problems of our time, and I'll try and explain why I believe that. That claim hinges on two sub-claims. The first is that deep learning will become a general-purpose technology, somewhat like steam, electricity, or computers. The second claim is that mathematical theory is actually useful to designing, building, and controlling that general-purpose technology. So this talk is not really going to address the second claim. That will come in future talks. What I want to talk about today is why you might believe that deep learning is a manifestation of some deep phenomena, and not just, as it appears, some set of ad hoc recipes that happen to work and just could stop working any time. That is, well, obviously the algorithms that are out there will keep working, but maybe progress stops tomorrow for reasons that aren't entirely clear. Why should you believe that the incredible progress that's been made in the last decade can continue? Okay, so that's the topic I want to address. Let's see. So this is Richard Trevithick's Puffing Devil, which is generally regarded as one of the first steam-powered locomotives. There's an excellent podcast about the first industrial revolution that you can listen to find out more about the story behind the Puffing Devil. But this happened in 1801, and you can see that in this graph, the takeoff of railway passenger journeys didn't really happen until, say, the 1830s, 30 years after this first engine was developed. So you could ask why, or more to the point for this lecture, you could point at that Puffing Devil and say that, it was just a toy. And that would have been accurate at the time. I mean, if you looked at it, it delivered small amounts of unreliable and dangerous power. Go listen to the story to find out about the dangerous part. At high cost. And it wasn't clear that it could be scaled up to actually do anything useful if it was just a curiosity for Sunday fairs. Okay, so in 1801, it's not clear that the Puffing Devil is going to obviate horses anytime soon. But we know from the benefit of hindsight that in fact there was no fundamental obstacle to scaling up the Puffing Devil's engine to much higher volumes and pressures and thereby delivering much more power. And that wasn't just luck, at least we can see that from the position of the future. We now know that there's a theory, thermodynamics, according to which if you analyze the Puffing Devil and look at what it's doing, you can understand that in principle there is no obstacle to scaling it to much higher pressures and volumes and therefore more power. Of course, the engineering involved might be very difficult. In fact, it was. A lot of material science was necessary, improvements in the manufacture of steel, improvement in the precision of parts. All of that had to happen, and that's why it took 30 years. But from an abstract point of view, there's no reason that you can't scale Puffing Devil up to a locomotive. Of course, we know that. We built them. But in the situation of deep learning, we're maybe in the position, maybe not quite of 1801, but maybe 1810 or 1815. We've built these things, that is deep learning systems. They work, but there's a lot of skepticism about whether they can, scale by another 2 or 3 orders of magnitude and start doing something really, well, it's already useful, but dramatically more useful than it is right now. But I think that situation of agnosticism being the sort of appropriate position to take regarding deep learning and whether or not it can scale to much more performant systems, that agnosticism really is no longer the rational position, in my opinion. And that's a consequence of a series of papers starting in 2017 on power laws. So this is the first one. Deep learning is scalable. Deep learning scaling is predictable empirically, out of Baidu. And then there was another paper in 2020 from OpenAI, perhaps better known, on scaling laws for neural language models. And it's this phenomenon of scaling laws or power laws in deep learning that I want to discuss. So maybe I'll say what a neural language model is. So basically the only kind of deep learning model that is relevant for this talk is a transformer. I won't explain what that is, but it's a particular kind of architecture. It was invented in 2017 and has become used for many different tasks, but it was originally invented and used in the setting of natural language modeling. So you take a very large corpus of English language off the internet and you predict the next word in chunks of text. That's the task that the model is trained on. And what was observed in this paper was that some of the properties of these models obey power laws. So I'll say briefly what a power law is. So a power law is just a relationship like the first line here. Y is the dependent variable, X is the independent variable, and Y0 is some constant. So after some shift of the Y value, Y is a power law function of X with some constant C and exponent gamma. Now if you take a logarithm of both sides, of course that's a linear relationship between the logarithm of Y and the logarithm of X. So that's usually how these things are plotted. Okay, so I'm going to show you some of those plots in the context of deep learning, where Y is the test loss, so the performance of a trained model on some held out set of data, and X is some other quantity. It may be the size of the model, it may be the total amount of compute that's used to train the model, it may be the size of the data set. So these are the kinds of power laws we're going to see. So this graph is a very important graph of the 21st century. So this is from the GPT-3 paper. It shows you power law behavior for validation or test loss of a trained transformer model on a large corpus of English and other language text from the internet against compute. I'll explain what the x-axis is exactly on the next slide, but for the moment just think about how many cycles you spend training this object. You'll notice there's several curves. Each color is a different model with a different number of parameters, and the relevant thing that obeys the power laws is the lower envelope of those curves. That's that dotted straight line. Okay, and you can see the formula in the bottom left for L, the test or validation loss, is a function of C, the compute, and that's a power law relationship. Okay. Okay, this is not a scenario I envisaged. Lavender, can you get him off my head, please? That's going in the video. All right. Okay, how can I get back to power laws after that? Okay, so that's a power law relationship, obviously. Look at you in the audience. Okay, let's get this under control. Okay, so that's an example of a power law, and the yellow line there is what people usually mean by GPT-3. This is the very large model with 175 billion parameters. Okay, so the x-axis, it's a bit of an awkward metric. It's petaflops, petaflop days. Petaflops means, so a flop is a floating point operation. So it's flops is the unit, floating point operations per second. So the reason they do it in petaflop days is that roughly one petaflop day is about 32 V100s running at typical efficiency. So that's a V100 is a part that costs more than 10,000 US dollars. It's one of the most popular data center GPUs. So if you go back and look at that graph and think about the numbers, you'll see it wasn't cheap to train GPT-3. Okay, so that's an example of a power law. Okay, so we've discovered these power laws, or OpenAI has. I'll say more about how universal they are in a moment, but it's not only language. So here's a sort of schematic of basically maybe what you could describe as the history of deep learning. So pre-2010, the size of our models and the size of our data sets was too small to see any advantage of neural networks, so people thought they didn't work. Then in the 2010-2020 sort of time frame, well, it started to work because data sets were large enough and compute was large enough. Maybe the point is that this power law behavior, if we go back, this power law behavior, well, it's present everywhere on this slide, but there's somewhere to the left of the beginning point of the x-axis where it doesn't hold. So the power law doesn't hold for all values of the x-axis. There's some, in this graph, the small data region, where the power law hasn't kicked in yet. And that's where we were until about 2020. So we just didn't know there was this power law behavior. But now we've hit sufficient size in those various quantities to see the power laws, and now we see them everywhere. I'll say more about that in a moment. But we're now on this power law region where the log-log graph is a straight line. And we get predictable returns to increased scale. And that's quite significant in terms of predicting the future of this as an industrial technology. So if Adam's here, maybe he can comment at the end of the talk about that. So in a couple of weeks, we'll hopefully have a talk from Adam Dorr, who's an expert in this kind of technological disruption. And this predictable returns to increased scale is one of the things that's kind of significant there. At least that's my understanding. Okay, maybe I'll skip this because I'm running out of time. But this is a brief run-through of the math involved in deriving from the form of the power law given in the GPT-3 paper the fact that at any value of the loss, once it's on the power law curve, if you want to decrease the loss by a factor of 5%, you need to triple the amount of data, roughly speaking. Okay, so once your data gets pretty big, that starts looking pretty intimidating. So there's a phenomena of decreasing returns, obviously. So that might seem, insane, right? So you can't triple the amount of data on the internet once you're already training on a sizable fraction of it, at least not, wait a few years and it'll triple, I suppose. But so maybe that seems like it makes the power laws a curiosity, but not something really very meaningful. But the thing to keep in mind is that not every 1% decrease in the loss is equal. So the task here is a very difficult one. It's modeling a huge corpus of language from the internet, all of Wikipedia, many book corpuses, many other sources of text, in the case of GPT-3 on language. To correctly predict the next word in every sentence of that corpus is an incredibly difficult problem. It's so difficult that to do it, once you get down near the bottom of that curve, that is the loss curve, once you get low down on that curve, each 1% improvement is a very, very difficult thing to eke out and requires surprising qualitative improvements in the, let's say, understanding of the model, keeping that word, who knows what understanding means. As examples of that, I'll show you a graph of the multiplication performance of GPT-3, trained on just text, but it needed to figure out basic arithmetic in order to model correctly that corpus. There's some very interesting examples of just asking GPT-3 to complete a list of symptoms and getting a diagnosis. Now, obviously, I don't recommend that you do that, but it's quite remarkable. This thing really has extracted a lot of rich information from our digital exhaust on the internet. And finally, I'll show you some pictures of some image GPT-3 work that just came out a few weeks ago. Okay, so this is a graph of arithmetic performance in GPT-3 from the GPT-3 paper against parameters. So the graphs I showed you before were power laws with respect to compute, but there's also a power law behavior with respect to the number of parameters in the model. We're not looking at a power law here, but the effects of that power law, the qualitative effects of just asking for the model to better fit the target distribution on that very difficult task. And as you do that, and if you follow, so imagine there's a power law going from left to right where the loss is dropping. And as you get near the end, this very large model just basically suddenly figures out how to do addition and other arithmetic operations. It's not being trained to do that. That's just a side effect of the task. Okay. Okay, so here's something called the scaling hypothesis. This term, I believe, was introduced by Gwern. He or she, they have a very interesting web page. I encourage you to take a look. The scaling hypothesis, to return to the puffing devil, is the hypothesis that deep learning is a manifestation of a deep phenomena, and apart from difficult engineering, that there are no fundamental obstacles to scaling to much more capable systems of the same kind. Now, we don't know whether the scaling hypothesis is true or false, but nobody knows. Despite many authorities appearing to be sure, they don't know either. And you could have been agnostic about this question 10 years ago, 5 years ago, but I think if you're being honest and paying attention, there is now some evidence for the scaling hypothesis. That doesn't mean it's definitely true, but you should start to take it quite seriously. And that means, well, obviously the ramifications of that could be quite profound. And if it's true, it means that this phenomenon and the underlying theory which explains it is a very interesting problem, obviously. Okay, so transformers started with natural language. They were then used for images beginning in 2019, but really dramatically, actually just in the last few months. You may have seen the news about protein folding from DeepMind. That architecture made important use of an equivariant transformer with respect to some Lie group. And people are starting to apply transformers to theorem proving, and indeed there are power laws in there too. So, yeah, that's a bit interesting for us. Okay, so I want to show you some more examples of power laws. This is a 2020 paper which was looking at applying basically the same architecture with minor changes to other domains, not just text. So here you can see the graphs, and there's just power laws all over the place. So there's power laws for modeling images of various sizes from ImageNet. There's power laws for translating text to images, images to text, power laws for video, language, math. This, I don't believe, is theorem proving. It's some other math problems. Okay, so the resource costs here are quite extreme in some cases, right? So this is not easy to scale up and get increasing performance. But if the results are there and they're economically useful, then you can expect that people will do this scaling. So the next decade is going to be interesting. So the question we're studying in the Melbourne Deep Learning Group, or one of the questions, is what fundamental theory explains these power laws? So there's some very interesting mathematics behind that, we believe. So maybe I'll just make a brief comment generally about why theory might be useful. So there isn't a lot of theory at the moment, and certainly when it comes to power laws, there's almost none. So maybe we don't need a theory. And if you're familiar with the history of the first industrial revolution, you'll be aware of the fact that, well, the final form of thermodynamics didn't arrive until, say, 100 years after the first engine started being built by, I forgot the name of the first one, but by Bolton and Watts. Oh, that's very irritating. Anyway, thermodynamics came quite a bit later, but a lot of the early practitioners were using the theory of vacuum and their understanding of mechanics and many other principles from physics to design and understand the results of their experiments. So even though thermodynamics as a final theory didn't arrive for quite a while, theory was still quite important. So maybe for two reasons. Theory reduces the number of experiments that you have to do, because certain ideas for heat engines or telescopes just can't work. And secondly, theory gives you courage, right? I mean, if you knew there was a theory, I mean, if people in 1801 had been sent back in time a thermodynamics textbook that told them that in principle it was possible to scale that thing up by several orders of magnitude, I think it's quite likely that that graph you saw with the takeoff in 1838 or 1840 would have happened much earlier. If you know it's going to work, then you'll invest the capital to develop the steel and precision instruments to build it. And in fact, that's already the case with the power laws I've discussed today. So the reason Microsoft built a billion-dollar AI supercomputer for OpenAI and why OpenAI is spending all of their money on these experiments is because they saw these scaling laws, and so they have confidence that they're not just going to throw all this money in a bin. They'll actually get some results out of it. Okay, so the 2020s are going to be pretty interesting, I think, as a result of these power laws. And I'll just show you some pictures to finish from some of the recent results. This is DAL-E, which is, if you recalled on the earlier slide, there was a power law for image to text. Okay, so if you saw that power law, you might think to yourself, well, let's spend a few $1 million to train a very large model to do that, to translate text to images. And in fact, that's exactly what OpenAI did. The architecture hasn't been made public yet, I believe. But this is the result. So you can, if you Google for DAL-E, you can find the web page and you can click on these underlined texts and switch them around and get sample outputs. So this is quite impressive, right? So it's combining armchair and avocado and many other concepts in a sort of plausible way to generate an image. And you can look through the other examples. This is something that wasn't possible a few years ago. Maybe there was early hints of this. Generating images from a data set, say from a data set of photos, is one thing, but being able to sort of combinatorially combine different concepts and objects reliably is quite interesting. And there's another one. So you can have fun with that. Okay, so that's the end of the talk. So what we're going to do now is have questions, so feel free to open up your mic and ask a question. And then we'll, so maybe after 10 minutes or so, we'll move on to the challenges. Okay, you see the challenge board. There are 2 challenges. Okay, so challenge 1 is ascend the knot. Challenge 2, or B, is find 3 invisible Guqin players. So you better go. The challenge has started. First one to the top of the knot wins the prize. Guqin's a Chinese.
What's a Guqin?
So if you hear a stringed instrument, they're hidden around the middle. There's a consistent theme to where they're placed. So if you hunt for them, you'll find one, and then do the obvious thing to find the other 2. Oh, this is great. Nobody stayed behind to ask questions. What am I going to do? I didn't think everybody would go to the knot.
Everyone's waiting for someone else to climb.
Some of you are getting pretty close.
See where the stairs are.
MDLG Discord.
I think someone just Oh, Will got it. Okay.
Alright, I think I got to the top.
Okay.
I know what
Okay, well, second challenge is still open.